All right, let's dive into something that is quite literally powering your world right now, but you've probably never even thought about it. We're going to pull back the curtain on one of the most important, yet most overlooked, little heroes in all of modern technology.
So let me just start with a question for you. What is the one tiny component that acts like a silent gatekeeper, controlling the flow of power inside pretty much everything? Your phone charger, your laptop, your TV? Any ideas?
Well, the answer is this little guy right here, the diode. Yeah, I know, it doesn't look like much, but trust me, this thing is an absolute cornerstone of electronics.
Okay, so what is it? At its heart, a diode is a semiconductor that works like a one-way valve for electricity. The best way to think about it is like a one-way street, you know? Or maybe a check valve in plumbing. It lets the current flow through in one direction, but it totally slams the door shut if it tries to go backwards.
That's really the diode's superpower, being a one-way street. And if you understand how it enforces that simple rule, you've basically unlocked the secret to how so many of our gadgets actually work. So let's take a closer look.
So here you can see the symbol we use in circuit diagrams next to the actual thing. Now, every diode has two ends or terminals. The anode, which is the positive side, and the cathode, the negative side. And what's so cool is the symbol itself. See that triangle? It literally points in the direction that the current is allowed to flow. It's got a built-in arrow. How smart is that?
So if it's a one-way street, how does it actually direct all this electrical traffic? Well, it's not magic, it's all physics. And it comes down to two really simple states of being. We call them forward bias and reverse bias.
And this slide lays it out perfectly. When you hook up a positive voltage to the anode, that's the flat side of the triangle, the diode goes into forward bias. It's like flipping a switch to on. Electricity just flows right through. But if you flip it around and apply that positive voltage to the cathode instead, you put it in reverse bias, and instantly, that switch flips off. The diode acts like an insulator and blocks everything. That simple flip in polarity controls the whole show.
Now, it's not a completely free ride. To get a standard silicon diode to turn on, you need to give it a little nudge, a little bit of voltage to get over an internal barrier. Think of it like a tiny toll you have to pay to get on the one-way street. And for most diodes, that toll is right around 0.7 volts.
But how does it do this? I mean, where does this one-way magic actually come from? To get that, we have to zoom way in and look at something called the p-n junction. And this, my friends, is where the physics gets really cool.
You see, a diode isn't just one solid piece of silicon. It's made by taking silicon and adding tiny impurities, a process called doping, to create two different sides. On one side, you've got the p-type layer, which is doped to have little holes where electrons should be. That makes it positive. On the other side, you've got the n-type layer, which is doped to have extra electrons, making it negative. The real magic happens right where these two sides meet.
So check out how this barrier gets built. The second you join these p and n layers, those extra electrons from the n side just rush across the border to fill the holes on the p side. When they meet, they basically cancel each other out, and this little flurry of activity creates a thin barrier right at the junction, which we call the depletion region. It's a neutral zone with no free charges, and it sets up its own little electric field. This creates this really cool equilibrium, like a perfect tug-of-war. You've got diffusion, which is the natural tendency for charges to spread out, trying to push more charges across, but that electric field we just mentioned is pushing them right back. In its natural state, it's a perfect stalemate, and that's the barrier that stops the current. When we apply voltage, we're basically helping one side of the tug-of-war win. So that's the physics behind the one-way street. And what's so amazing is how engineers have taken that one simple idea and created a whole family of different diodes, each one specialized for a very specific job. Let's meet a few of them.
So you've got your basic rectifier diode. That's the workhorse that turns the AC power from your wall outlet into the DC power your phone needs. Then you've got the superstar, the LED, the light-emitting diode, which, you guessed it, gives off light. It's in your TV, your light bulbs, everywhere. Zener diodes are kind of weird. They're actually designed to let current flow backwards at a very specific voltage, which makes them amazing circuit protectors. And then there are photodiodes, which do the exact opposite of an LED. They turn light into electricity. That's the science behind solar panels.
So yeah, from converting power to actually creating light, it's pretty clear just how critical this tiny component really is. It is, without a doubt, the unsung hero of our electronic world. Honestly, this quote just says it all. Without diodes, modern electronics would be nearly impossible. I mean, just let that sink in. They are absolutely fundamental to almost everything that we use every single day.
So, let's bring it all back.
When you think of a diode, just remember that gatekeeper. Its job is to convert power, to protect our delicate circuits, to light up our world, and even to turn sunlight into power for us. They are the silent, microscopic workers that make our digital lives possible. So I'll just leave you with this final thought. The next time you see a tiny light turn on or a motion sensor go off, just ask yourself, is that a diode turning electricity into light, or is it one turning light back into electricity? Because with diodes, both are happening all around you all the time. Thanks so much for tuning in.